Hello, and thank you for joining us today for the Observability Trends webinar series. I'm Grant Swanson, and today we have Christopher Milton, Solutions Engineer at Observe, who will be showcasing how Observe solves the high cardinality problem. Welcome, Chris.
Thanks, Grant, and welcome to our webinar, Solving the High Cardinality Problem with Observe. I'm Chris, and today we're going to tackle a major challenge that many organizations face, managing high cardinality data. Now, whether you're familiar with this term or this is all new to you, by the end of today's session, you should have a clear understanding of what high cardinality is, why it's an issue in IT observability, and how platforms like Observe can provide effective solutions to handle it. So here's a quick overview of what we'll be covering. First, we'll start by defining what cardinality is and why it matters in observability. Then we'll dive into how cardinality affects different types of data, like logs, metrics, and traces. After that, we'll explore how Observe solves high cardinality problems effectively, and we'll follow that with a section on best practices for managing high cardinality in legacy platforms. So how do we define cardinality? Well, cardinality is a measure of the distinctiveness or uniqueness of values within a specific data attribute or dimension in an observability system. It reflects the number of different values that can exist for a given field across all collected data points. Basically, cardinality refers to the number of unique values in a data set. For example, think of a field like HTTP methods. I'm talking about get, post, put, so on and so forth. There's only a few possible values that can be returned. So that's low cardinality. On the other hand, if you're tracking something like session IDs, every single session has unique value, meaning you're dealing with high cardinality. In observability, the more unique values we track, the more complex the data becomes. This increase in complexity can slow down queries and increase storage costs. So let's make this a bit more relatable. Imagine a coffee shop that tracks sales. If they only track how many coffees they sell each day, that's low cardinality. It's a simple count. But when they start recording what types of coffee are sold, espresso, cappuccino, so on, the complexity increases, creating a more moderate level of cardinality. Now, let's say on top of that, they also want to track loyalty card IDs, drink preferences, and payment methods for each purchase. Now, this is a much higher cardinality because each purchase adds a new layer of uniqueness. In IT observability, this complexity is similar to what we see in cloud-native environments today, such as AWS, Azure, or GCP, where millions of unique data points are generated. Now, it's also worth mentioning that cardinality is introduced differently depending on the type of data we're dealing with. I'm talking about logs, metrics, or trace data. In logs, for example, high cardinality fields like transaction IDs or session IDs can add to cardinality, making querying the logs slow and expensive. With metrics, having many unique labels, for example, like server regions, customer segments, job IDs, or pod IDs, can explode cardinality, making monitoring systems struggle. Now, for traces, distributed systems that span multiple services generate complex, high cardinality trace data. And we'll touch on that more in just a second. But understanding how cardinality impacts these data types is crucial for finding the right solutions. So let's talk about distributed systems. Distributed systems are where high cardinality truly becomes a challenge. As these systems grow, each service or node generates its own unique set of metrics, logs, and traces, which cause the number of unique data points to increase exponentially. This isn't just about the number of nodes, but also the relationships between them, like cross-service communications or dynamically created instances like pods. When these systems scale up or down dynamically, they generate even more unique data points. And each new service instance or transaction introduces additional complexity. The ability to monitor, track, and understand the performance of such systems becomes much more difficult without a platform that can handle this data efficiently. So let's talk about how Observe efficiently handles high cardinality data. Now, Observe is built to scale, allowing for very large ingestion amounts of up to a petabyte per day. This means it can manage vast amounts of high cardinality data, ensuring that performance stays consistent even as data volumes continue to grow. One of the key innovations that makes Observe so efficient is the decoupling of storage from compute. In many traditional systems, storage and compute are tightly linked, meaning that as your data grows, you're often forced to scale both, leading to unnecessary costs, especially when you're not actively querying the data. With Observe, storage scales independently of compute. You can store vast amounts of high cardinality data at a low cost and only use compute resources when you're actually querying or analyzing that data. This flexibility leads to significant cost savings, especially when handling large data sets that may not require frequent querying. Additionally, Observe employs highly efficient columnar storage and compresses data by up to 10x, which further reduces the amount of storage required and lowering all overall costs. These technologies make Observe a powerful solution for handling high cardinality data at scale while keeping costs under control. There's another game-changing feature of Observe that significantly aids in managing high cardinality, and that's schema on demand, which deserves a deeper dive on its own slide. So schema on demand, it's a defining feature of the Observe platform, and it's an incredibly powerful approach when dealing with high cardinality data. One of the most significant benefits of schema on demand is its flexibility. It allows the schema to be applied at the time of data retrieval rather than during ingestion, which means that you aren't limited by predefined structures when you store data. This makes it much easier to work with evolving data sets, particularly those with unpredictable or dynamic high cardinality fields. With Schema on Demand, you can ingest raw, unstructured data rapidly. And this is crucial when working with high cardinality data sets, as they often contain a wide variety of unique and diverse values. By storing data in its native format, you preserve all of those unique values without forcing them into a rigid structure, which is essential for maintaining the full scope of insights. Another major advantage is the ability to apply multiple schemas to a single data set. Now, this is incredibly useful when different use cases require different views of the same data, especially in high cardinality environments. Instead of duplicating the data for each view, you can tailor schemas to each specific analysis need while keeping storage requirements low. And finally, Schema on Demand excels in exploratory analysis. Since the schema is interpreted dynamically, you can adapt on the fly as new patterns of high cardinality fields emerge. This adaptability means you're always able to stay responsive to the changing data without needing to adjust the underlying storage. By leveraging Schema on Demand, you gain both the flexibility and performance needed to efficiently handle high cardinality data. So let's take a look at how Schema on Demand actually works within the platform. So in Observe here, I'm in our Log Explorer, and I'm viewing raw container logs coming from Kubernetes. Now, I'm going to go ahead and do some light filtering on these logs to surface log lines that would be a good example. I'm going to select a specific namespace, and I'm going to do a keyword search to bring up some specific log lines. So we have these log lines up here. I can go ahead and double click on one of these, and we can see that the log information is actually an unstructured text string. But I see some fields in here that could be very useful to me in my schema. For instance, user ID, product ID, and quantity. So what I'll do is I'll go ahead and leverage one of Observe's AI features here. Well, I'll say I want to extract from this string. It's going to comb through this log line here, and it's going to pick out fields that it can extract. I'm going to go ahead and select the fields that I want, namely user ID, product ID, and quantity. I'm going to hit the Generate Regex button to have Observe create the regex entry to extract this data. I'm going to click Apply, and those fields now appear directly in my schema. User ID, product ID, and quantity. Now, let's say I want to take this one step further. Let me go ahead and open this in a worksheet, and we'll further enrich this schema dynamically. Now, I have this product ID column, and I don't have the actual product names anywhere in this log. But let's say I want to show that in my log. Well, I know I have another data set that has these product IDs and product names together. So what I can do is I can go ahead and link our data here to another data set, our product data set here. And I'm going to link this on our product ID column. And we'll call our new column here product. So now we're going to correlate the product ID that we have in our logs to the product name in that other data set and marry the two together in this schema. So now I'm viewing actual product names. Now we can go even further than this. I can bring in additional fields from that other data set into my schema where this information previously did not exist. I'm going to go ahead and select add related fields. I'm going to select price, hit apply. And this is going to bring the pricing data for those items directly into our schema. So using schema on demand, we've extracted fields from a unstructured text string, brought those fields into our log here. We've pulled in another data set that we've linked to this one, and we've correlated the information, namely product ID, to the product name and brought that information over. And on top of that, we pulled in additional data from that alternate data set, pricing information, to further enrich our schema. Now, the cool thing about this is that because we're not applying a rigid schema to this upfront, I have this completely new, unique view, and I'm not duplicating any of this data. I'm simply applying a new dynamic schema to it as I'm performing whatever analysis I'm performing. So let's say you're not on one of these modern high-performing platforms designed for high cardinality like Observe. Managing high cardinality in these legacy platforms can be challenging, but there are several proactive strategies that can help reduce its impact on your system. Let's go through some key features and practices you can implement. First, it's essential to identify the sources of high cardinality in your environment. By using monitoring tools or dashboards, you can pinpoint which metrics and labels are contributing most to the problem. This allows you to focus your optimization efforts on the areas that will have the greatest impact. Next, optimizing label usage. It's critical. You want to be strategic about the labels you define. Make sure you're only using relevant labels that provide meaningful insights and enforce consistent naming conventions across related metrics. In some cases, dropping or relabeling high cardinality labels that aren't crucial can simplify your data set without losing valuable information. It's also important to implement efficient data collection practices. Now, this could mean filtering or sampling metrics from a subset of events rather than collecting the data from every single one. Aggregating metrics at a higher level, like service level metrics instead of individual user level metrics, can significantly reduce cardinality without losing key insights. And defining retention policies can ensure that detailed metrics are only kept for a short time, while aggregated metrics are stored longer for long-term analysis. When it comes to querying your data, using smart querying techniques can help minimize the cardinality you're working with. For example, functions like top K and bottom K allow you to limit the number of returned data points, focusing on the most relevant ones. And by writing targeted queries that focus on specific label combinations, you can avoid querying all possible combinations, which keeps the system performing efficiently. Lastly, reviewing and optimizing your setup is important. Over time, high cardinality data can accumulate. So periodically assess the value of your metrics and labels. Remove or modify those that are no longer providing meaningful insights. Observability is an ongoing process, and staying updated on best practices will help ensure that you're effectively managing cardinality. So to sum it all up, high cardinality is a major challenge in IT observability, but with the right approach, it can be managed effectively. We've discussed how Observe tackles high cardinality with scalable data ingestion, flexible data handling, and cost-effective storage solutions. And while best practices can help mitigate some issues, switching to a modern platform like Observe provides a much more robust solution. If you're ready to explore how Observe can help your organization manage high cardinality data, feel free to reach out to us for a demo or more information. Thank you so much for